So at this point, I'd like to point out some of the vulnerabilities that containers come with by design, at least by implementation, which is a virtual machine usually goes a long way to isolate workloads between virtual machines. So that could be a fully virtualized virtual machine where even the actual processor is virtualized, so that, for example, you can emulate a Commodore Amiga on a Raspberry Pi, right? So how do you do that? You really need to emulate the processor there in order to run the RISC commands that such an Amiga processor would use. Whereas our x86 and x64 processor architectures are, different instruction sets, different processor architectures, so they would be different. Now, if you go a little step less and you have para-virtualized machines, then usually the hardware exists to create little protected spaces of memory, so where you still have a lot of isolation, but you don't have the same degree of freedom of choosing a different processor architecture. I'm not a professionalist in particular virtualization structures, but I think the picture is all right here. So if you're on a virtual machine and you're starting a Linux virtual machine within a Linux host system, you could, for example, have a SUSE Linux as host system and use Ubuntu as a guest system. And as you can see, that this will implicitly require that you'll import and load another kernel. So that's where you add memory overhead. So the memory overhead of a virtual machine, as said before, could be several hundred megabytes. And because you also have to, set up all the software packages required for a base system, which for a modern Linux distribution can easily be hundreds of megabytes too, if not gigabytes, then you also add storage overhead. And we also mentioned that it takes quite a time to start such a virtual machine. So the original concept of a container is different. It doesn't use a hypervisor. It doesn't emulate a processor architecture, and it doesn't even load a different kernel. What it does, it uses concepts that have been introduced in the Linux kernel a few years ago. They're called namespaces and C groups, and they allow you to create a little bubble around a process that will shield one process from another, particularly when it comes to CPU and memory. So what you want is you would like to prevent that one of the processes, let's say the cluster manager of our database example, or the database daemon itself, consumes all the memory of the virtual machine and just then, dies away. So you'd like to have them isolated in two different containers. And each container will impose restrictions on the process so that if the process stretches beyond that scope, then the container will collapse and restart. So we can see that this has some sense. It's also very fast because you don't have to bootstrap an entire operating system. Such a container can be started in less than a second. So assuming that the container image is present on the host system in this case. So it can be very, very fast. But there's a drawback because there's no disk I/O and no network I/O isolation at this point. So for example, if you have two co-located databases, they still use the same disk, and they still use the same network interfaces. Well, this means that one database could draw down the performance of the other one. So isolation in containers is not 100% safe. There are ways to work around that, but let's say in general, a container is not as well isolated as a virtual machine, but therefore it's blazingly fast, and it has the advantage of that standardized container image. There's another very important gotcha with containers. Let's go back to that database example. So you've created your, let's say, Postgres cluster. Well, let's make it even easier. A single Postgres container. So you created the container image with Postgres or downloaded it from a registry and started up. You insert some data using SQL commands, and you'll shut down the container and restart it. Well, that's when you'd be surprised because you can't restart it in the first place. You can't restart the container. Well, this may be different for different container daemon implementations, but the container, once it's stopped, is terminated. It's not paused, it's terminated, which means that the memory state is lost, and also that anything your database has written to the file system is lost. Who of you is surprised by that? Give me your opinions. What do you think about this? How is that confusing, or did you already know that?
I already knew.
Ah, wonderful. Why is that? Would be the next question. It's one thing to acknowledge that it is the case, but why would you do that? Any ideas?
Maybe it's a design choice, so it's easier to I don't know, create new machines or create large groups of machines. Like you don't have to manage the state, which takes a bit of responsibility from away from you as the developer.
I think that's the right direction. Look, if you manage a container and the container has state, we are in. Well, let's take the Kubernetes example. In Kubernetes, you will see that a cluster is spread across several virtual machines or several physical machines, which means that there's what we call cluster nodes or Kubernetes nodes. So a container could be co-located on one of the nodes. There are certain qualities you want to achieve in such a system. For example, you would like to be able to maintain it, which means that you also at some point have to update Kubernetes itself. The underlying infrastructure has physical hosts, and they could fail at any time, so you want to have resiliency against node failures. And the question is, how do you add resilience in that particular case? And the answer is, you need to be able to move a container across a cluster. And when I mean move, I mean let the container fail and deal with the failure gracefully. Dealing with a container failure gracefully means that you should be able to start the container somewhere else in the cluster without worrying that it has recently failed. So in a system like Kubernetes, we will see that you'll have a declarative approach. You basically describe how your distributed workload should look like. So I want to have a database, one node there. I want to have an application, one node there. I want to have this part of the application, 3 nodes. This is what you describe. You hand over this specification to Kubernetes and let it go. And Kubernetes will create the containers and also keep those containers running. Now, if one container fails, it will say, oh, there's one container missing. I'm going to restart it. You don't have to do any actions. It will be done for you. And in order to make that possible, the container orchestrators often require a workload to be stateless. That means your web application, for example, let's consider a Facebook clone, because this is an application that usually anybody knows from the user experience, or from the user's perspective. So one of the things you do in Facebook quite a lot is you upload pictures. So if you, for example, add a new profile picture, you have to store it somewhere. And one of the locations where you don't want to store it, because the container is stateless, is in the file system of the container. And that has the advantage that all you will store in the container is the application code. So where do you store your image instead? Well, I'm giving you the answer. It's an object store, such as Amazon S3 or OpenStack Swift. You don't put it on an NFS or something like this 20-year-old technology that won't scale horizontally. So definitely want to go with a horizontally scalable object store of some kind. So you put the asset where it belongs, into a system that's designed for that purpose and that has operational qualities that are much better than a container. And it is consequently that you'll get a lot of free lunches in terms of very good qualities from Kubernetes, for example, if you let your container be stateless. Now, if you're familiar with Docker, you know that Docker has volumes, and a volume has a different purpose, at least in my interpretation of volumes. You can mount an NFS store into a container, which to me is an anti-pattern. Why is it an anti-pattern? Because NFS is limited in scale. Well, there are high-end storage systems that can be very, very large, and they can be good enough for certain use cases. But if you look at Facebook-style solutions, I'm pretty sure you won't find an NFS in that architecture. You will find an object store that scales horizontally to the end of the world. And the same is true for databases. But you don't use an object store for a database, because a database inherently requires a block device to write and read from. It's because the database itself uses file formats that make for, let's take, you have a table and you store your relation somewhere, and you have indices or indexes that make looking up a certain piece of information from the database very fast. And all these structures are organized and optimized for disk persistency. So you need to provide your database a disk. So this is why volumes are attachable to containers. Most often, you will find an object, a block storage device being remotely attached to a container, so that the persistent disk or persistent volume is mounted in a container. Then you will mount that into a data directory of your database. You write your data to that particular volume, and when a container fails, no problem, because you create a container somewhere in your cluster and reattach the volume. So you'll have to provide a high-end storage somewhere, and you have to have a very, very fast broad bandwidth network connection, so that remotely attached volume won't eat much of your performance, which is currently, like 10 gigabits, for example. They're good enough for most of the databases. So in a container image, to come back to the container thing, is you'll have a layered file system. We'll look at that at some point too. It's overlayFS, tempfs, so there are several file systems mounted together, so that when you start the container, there's going to be a temporary file system, in-memory file system mounted on top of that. You can write to that, you can create files and do everything you do in a file, but if the container fails, everything is gone. If you want to have persistency, you'll have to add a volume to your container, and there persistency will be ensured for you. We'll also, discuss in more or less depth that a volume is not a volume. You have to be very careful where the volume is mounted and how it is provided to you, because this will determine what is the reliability of such a volume. But the main point and the main takeaway is a container has an ephemeral disk. It is volatile. It is gone when you terminate the container. So take that as a takeaway. It is gone when you terminate the container, and that makes the dealing with containers much easier at a scale of an entire cluster. The volume concept, we'll look at it a bit later.